Okay, well, welcome to the Pacific Planetarium Seminar on this lovely Friday, April 27th. And we have a guest speaker today. Mark Subbarao is going to be telling us a little bit about the IPS initiative for Data to Dome. And Mark Subbarao is the president-elect of International Planetarium Society. So, Mark, welcome.
Thanks, Alan. And yeah, I really appreciate the opportunity to talk to you. I think this, I'm really excited about this sort of idea for these online seminars. And I think this is a kind of community-wide education format that could have real impact. So I salute you guys for really initiating this at PPN. So the Data to Dome initiative, this is sort of a movement that has been happening over the last few years, and I think it's really taking off. So if I look at, you know, it started out with a handful of things, but now I look at the number of conference submissions to the Toulouse conference that are using the word Data to Dome, and I'm very heartened by the fact that this is really catching off. The idea really is that we, hold on.
Okay, Mark, can I interrupt you for a second?
Sure.
You have a button there that says start your video. Oh, never mind. It won't work anyway. I'm sorry. Sorry to interrupt.
You have it's crossed out, yeah.
Yeah, that's okay.
Okay, what does that do?
Sorry I interrupted.
Oh, no worries. But as a community, we've gone from this, and this is the original Adler Planetarium projector, and this is our upgraded projector. And so that's the transformation that we're all aware of that's happened in the planetarium community, and it's transformed what we're capable of doing. So we're now not just a planetarium, but we can be many things. Really, it's this networked big data visualization facility. That's one revolution, but an equally important. Yes?
Well, I think somebody may have come in and not muted.
Okay. An equally important revolution is the one that's been going on in science, and it's not just the data-intensive science, but it's the fact that more and more that data is open and available and accessible and networked, right? I mean, it wasn't too long ago that everybody was afraid to put their planetariums on the internet. That's still true in many countries, but connecting ourselves to that greater world opens up a lot of possibilities, and that's really what the Data to Dome initiative is about. So this is where I work at the Adler Planetarium. This is our little space where we sort of prototype our scientific visualizations. It's got a lot of toys that have been borrowed, occasionally purchased, and mostly stolen. Here's a little video I like to show of really what that kind of big vision is, of being able to interact seamlessly with data and immerse yourself in it. Before I go too far, I want to explain and apologize for a bit of really lousy nomenclature. And there are two things here. One that's sort of spelled out Data to Dome, and the Data to Dome with the number 2. And early on, the idea behind this wording, Data to Dome, was sort of like farm to table. The idea of farm to table food is if you can directly bring food from the farmer to your plate with this little stuff going on in between. Not only is it hopefully cheaper because you've eliminated a number of middlemen, but it's fresher and it's better for you. and you're getting higher quality things. And the same thing's true of data. If we can make it easier to bring that data from where it was detected, from the supercomputers that are running simulations, from the telescopes that are making discoveries, and to present it in the planetarium, the faster we can turn that around, the more immediate conversations we can have with the public. All these new possibilities are opened up. That was why it's called what it's called. The 2 with the number, we decided early on to attach to a format for announcing and distributing planetarium content, and to keep the 2 with the word for this general idea. That's led to a lot of confusion, and I humbly apologize for that. So here's some of the things that we thought we would accomplish, and part of the goals, and the main one is really to prepare the planetarium for this era of big science, right? And we're kind of in that era now because this thing just dropped on us, right? So the Gaia stuff, super exciting. Here's some numbers. That's almost 1.7 billion stars with positions. And parallax and proper motion for 1.3 billion. So we used to love to fly people around the Hipparchus catalog with 80,000 stars and tell them these are all the stars that have been mapped out. And we're going through the known universe. But something happened this week, and we went from 1 million or so to 1 billion, and we can't do it anymore. It breaks all of our software. This is a problem.
Is there an mission supervisor online?
I couldn't make that out.
Reminder for people
Go
to
ahead. We have an item of value in Boeing.
people should stay on mute if there's background noise, please.
All right, so this is breaking all of the software out there. It is possible if you're clever enough to visualize this many objects, but it's a real challenge. And that's just the start of it, right? So in addition to Gaia, the Large Synoptic Survey Telescope is being built. We're going to talk about petabytes of data. We're going to go from just observations of objects to taking movies of the sky. We're going to detect maybe 10 million things every night that have changed in some way. So there's this immediate stream, this constant stream of information coming. And then, these optical astronomy projects are dwarfed by the data volumes that we're seeing in the current and next generation radio astronomy projects, particularly the Square Kilometre Array, which is a really, really serious data and data visualization problem. But one thing that's happening is that as this data is getting bigger and more complex, it's not just a challenge, it's a challenge to visualize, but it's a challenge to understand. And as part of that understanding, visualization will play a more and more important role. And here's the sort of mathematical argument for that. So if we think of a visualization, which is labeled here as V, the amount of time it takes or the work it takes to create that goes as the order of, so this is the big O notation, roughly the number of objects N and the number of pixels in our display, P. We've been getting bigger and bigger displays, right? 2K Planetaria, 4K, 8K, 10K, but that's going to stop at some point. P doesn't scale forever, and that's a nice thing. That linear scaling is really nice because actually statistics naively square most statistics. If you want to measure clustering or something, is a square of the number of particles. If you're clever, you can get that down, but linear scaling wins out with big data. And in fact, if you're smart, you don't actually have to scale with the number of objects that you're trying to visualize. And that's because what you really are creating is you don't need to draw everything. What you really need to do is on your screen create a perceptually accurate drawing. And in many cases, like if we have a cluster of many, many particles all in one pixel, we don't have to draw millions of pixels. So that actually can increase that scaling even better. So if done properly, visualization wins out in the big data era as a way to explore data sets. So one of the things we also talk about is trying to establish some best practices for data visualization in the planetarium. And there's some science behind how to do that. This is a representation of results of a paper, a sort of seminal paper by Cleveland and McGill back in the 80s. But it was one of the first to really look at visualization and say, like, all right, we know that we can use the visualization to encode all kinds of data, but how accurately can we decode that? It turns out there's a hierarchy of how accurate we can do that. So going from the left to the right, you see sort of points, positions on a graph. We can read that very accurately. Things like length, angle, or orientation, less accurately than that, but still pretty accurately. Things like area of an object, less accurately. Volume or curvature, even less accurately than that. And things like color, saturation, and hue, even less accurately. And that's a challenge because we love to use color. But color has a whole host of problems, right? For example, that bar at the center is actually one constant color. You probably saw it as a gradient, but you're just fooled by the background image. You know, we are pretty lousy about using color in astronomy. So this is that famous WMAP image. Everybody recognizes these colors now as the CMB. But there are problems with those colors. When you looked at that image, the yellow really popped out, and that has to do with this quantity of luminance. We don't see red, green, and blue equally. So this is a parameter in this Jupyter notebook here, which is actually measuring how brightly our eye perceives things. And we're looking at different color maps. And you see that there are sort of peaks in some of these color maps. And this is really why that rainbow color map is very misleading. And in fact, actually, there are lots of different kinds of rainbow color maps. Some are better than others. None of them are great. Let me see. I'm going to show you one more of these. Color maps. This one is a perceptually uniform color map. And so these are a great thing to use if you're trying to demonstrate an ordering of objects, and the things on the right appear brighter than the things on the left. In the case of the CMB, what we actually want to do is measure deviations from a mean. So in that case, something like a diverging color map like this one is actually a better choice. Now, you might say, big deal, does that really matter? And the answer is, well, it can matter a lot. In some cases, you know, it can be life or death. So this is a study looking at some of the scientific visualization software that's used in medical imaging. And the takeaway is by doing a couple of interventions, one going from a three-dimensional representation to a two-dimensional representation, the other going from this rainbow color map to a divergent color map. Researchers went from detecting only 62% of these weaknesses in the aorta to 91%. So that's a pretty remarkable and kind of terrifying improvement. Despite that huge improvement, when asked which one they liked better, they all picked the way they were doing it before, the 62% accurate way. So if we look at the CMB, it's really a one-dimensional thing, so perhaps a grayscale color map is good. But again, what we really want to measure is deviations from the mean. We want to measure the hot spots and the cold spots. So this kind of divergent color map that is now used by Planck is now using a better map. is probably a good choice. But those are our considerations in using color with professional audiences. But when you're dealing with public audiences, there are other considerations as well. These are some interesting studies by the Aesthetics and Astronomy group, which is out at CFA, the Chandra Outreach Group. And in particular, they make color images out of X-ray data. Of course, we can't see X-rays, but you tend to make the shortest wavelength blue and the longest wavelength red. But that's not people's expectations, right? There's an expectation from every time we go to the bathroom, we're told that red is hot and blue is cold. So, so here they played with inverting that representation and seeing how well people understand that. Here's another example from one of the sky shows we made at Adler, and we had a survey, a flight through a simulation of large-scale structure. We started playing with some of the colorization, not initially to increase understanding, but actually to make things more visible. So we were doing that blue on white representation at the beginning, and then we switched to this inverted color mode just because it made it easier to see the structure. But it turns out Zoe Buck, who was a graduate student at the time, she's since got her degree in this formed part of her thesis, she was interviewing people after they saw the show and finding that they were confused about where the dark matter was. And in particular, they were confused because people expected dark matter to be dark, because that's what the word says, right? And so she did this study where she had people look at, we made 3 different colorizations of that visualization. She had people watch it, different ones, randomly online, and they had to ask different questions. The important part to look on this graph is to recognize the red as being correct. And you see people went from 24%, only 24% answering the questions right, to 75%, just by this change in colorization with the exact same explanation of the data. So our choice in visualization can make a huge impact in people's understanding as well. So it's not just how to show something as effectively as possible, it's also taking into account with a public audience what their biases are. And that information fed into the way that dark matter was visualized in the Dark Universe show by Eamon H. And for the life of me, I can't remember why I decided to show this movie. Anyway, one way to deal with, oh, now I remember. One way to deal with a good example of dealing with the big data problem exists in 2D, and Worldwide Telescope is a great example of that. It really comes down to the fact that you only need the data for what you're showing on the screen. So I can zoom in and zoom in and zoom in, but I don't need to download all of the information. This is how Google Earth works. This is how Worldwide Telescope works. So in this little fly-through, I'm going to zoom in by a factor of 1,000,000. By the end of this, the size on the screen of this imagery will be less than 1 second of arc as we zoom into this protoplanetary disk, HL Tau, that was imaged by ALMA, and then even a little smaller section that was imaged by the CLA. Part of the problem is solving things like Gaia is doing that in 3 dimensions. And the trick really is something like this. It's nearby, and here I'm showing visualization we did through large-scale structure, but when you know what the camera path is, and the camera path is along that green line, I only need the most accurate information nearby the camera. Farther away, I can use less accurate information, and further away, less accurate than that. So in the computational realm, they've been dealing with these kind of big data problems for a while. This is an interesting project called the dark sky simulation. And some of that has to do with how the data is stored. So by storing the data in this sort of space-filling curve, it means that you can access what you want very accurately. So for example, there's this online app, and you can even look at it in VR, called Halo World, where you can give it a number. This works in your phone. You get back a three-dimensional visualization of that part of the simulation. But what it's doing is actually, behind the scenes, reading from a single 32 terabyte file and pulling that back. And this all happens incredibly fast because it knows how to do it. One of the other things you really want to do is encourage the use of the planetarium for visualizing all kinds of scientific data, and maybe even more than just scientific data, but moving beyond astronomy. These are some images from a Neurodome project. You know, this is a fun data set to play with because you get really structures we don't get in astrophysics often. This is a couple of different visualizations of something called diffusion tensor imaging, which technically measures a three-dimensional tensor field, but what it gives you is neural pathways. Seismodome, which is a really interesting project, which combines not only some beautiful visualizations of both seismology data and simulations, but also sonifications as well. And with this capability to really provide sort of research grade visualizations, one of the things that we're really promoting is the idea of using planetaria as community-wide visualization facilities. And this could be a potential new use of the planetarium. It's not entirely a new idea. My institution, the Adler Planetarium, this was always at the core of the way people thought about it. When Max Adler founded the Adler, he wrote that with the aid of the Planetarium and Astronomical Museum, science may be advanced. Now, that was a kind of a lofty thing and sort of ridiculous in a way because, you know, this was 1930. You know, Hubble had just discovered the scale of the universe, had unlocked the secrets of the atom, and that machine wasn't capable of doing that. But maybe it is now. And so here's an article that Tom Kwasniewska wrote in Nature, really trying to reach out to the scientific community and invite them to use the planetarium to explore their data sets. There is a really important experiment going on in South Africa right now, and that's at the Aziko Planetarium and Digital Dome, where they built a facility that's partially a public planetarium, but partially a data visualization facility for local researchers. And Tom Jarrett is listening, right, Tom? He's online, and here we are at the opening with two of the ugliest ties you'll ever see.
Nice job, Mark.
Thanks. I love that photo. And I was back there again a few months ago for the dot astronomy workshop, and had a pretty cool hack day, and here we are flying through some, this is actually Galaxy Zoo data sets. And the other part has to do with standards and trying to take advantage of the fact that so much is changing in astronomy so fast, and new discoveries are happening all the time, and it'd be really great to be able to talk about them when they happen. And we can do that, and this is the data to dome format. And in the chat window, I put in a couple links. One is for datatodome.org. So if you're interested in that, I encourage everybody to sign up. But this standard is really a way for content providers to announce what they have, and for that to show up automatically in the planetarium. And this is the interface in one particular piece of software. You see all the new images, you can select them, you can download them, you can place them on YouTube. And so, this is now running in the, well, here you see it in Sure Universe, but in Digistar 6 from Evans and Sutherland. But I think almost all major planetarium manufacturers are working on incorporating the standard. So I expect by the IPS meeting, we'll have almost full adoption in the community. And, one of the other great things is really linking planetariums together. And that's one of the things that we've been promoting at Adler through dome testing. In particular, we have these series of lectures with prominent scientists and called the Cobley Full Dome Lectures. We've also started streaming those to VR devices. So here you see a young lady at the Chicago Children's Hospital who's able to watch the lecture from her hospital bed while it's happening live. And here you see a group in New Zealand watching the same lecture, our last lecture with Lisa Kaltenegger. We have another one coming up May 9th, and I hope you all are able to join. So that's a little rundown, but I think the really the great thing about these seminars is the opportunity to chat about stuff. So I'm gonna take away the screen share, and then hopefully maybe we can flip.
Actually, I like to break the recording up into two parts. Sort of my idiosyncrasy. So I'm going to stop the recording.